Okay, so what we're going to look at here is a little bit of review of vectors from Science 10, but that's going to take like 5 minutes because, well, we basically only did positive and negative, forward and backward kind of vectors in Science 10. What we're going to look at is the fundamentals of vector addition, especially how do we draw vector diagrams? How do we resolve a vector into its components, which is something you never had to do before, right? If you have something going 10 kilometers due east, it only goes east, right? It's only got an east component to it. But if something goes northeast, then it's going somewhat north and somewhat east. And you would have to find out how much does it go north, how much does it go east. Those would be its components. Okay, we would look at them as the horizontal or easterly component and the vertical or northern component of that particular vector. Right, so that's what we're going to be looking at today is how to resolve a vector into its x and y horizontal and vertical components, okay, and what that's going to look like. Right, so the first off, the easiest vectors are collinear vectors. They're the vectors you dealt with last year. Okay, all the one-dimensional forward and backward, north and south kind of stuff. Okay, we're going to look at all vectors being added by placing them tail to head. This is how we draw vectors. How do we represent a vector quantity visually? Right? And then understand that vector quantities obviously have magnitude and direction. There's your quick review from Science 10. We've already talked about that like 3 times already. Okay? And understand that all vector quantities are added the same way. People get stuck on this. Right? And they get stuck on it because when we first start out adding vectors, it's always displacement. We're saying this person went this far in this direction, then they went this far in this direction. And people get the idea that you only ever add displacement. And that's the only vector quantity we add. And then I give them 2 velocities to add together and they don't know how to do it. Or they go back to doing it a different way. Any vector quantity, displacement, velocity, acceleration, force, they're all vector quantities and they're all added using the same technique that we're going to learn today. Okay? We draw them out, we put them tail to head. All right. So, a vector quantity has both magnitude and direction, and because direction is an important characteristic of any vector quantity, okay, we have to use arrows to represent it. Okay? It's logical to use an arrow to represent a vector quantity. Now, the convention is this. The length of the arrow represents the magnitude of the vector. So if I had a 5 kilometer vector and a 10 kilometer vector, their arrows would be different lengths. A 10 kilometer arrow would be twice as long as the 5 kilometer arrow. Okay, everybody with me on that? That's kind of logical to do.
Would that be like on a graph? You put the arrows in?
No, this isn't actually on a graph at all. So we're like done graphing. We're not even looking at graphing now. We might, if you want, you could like draw it on graph paper if you wanted to, but it's not to do with position versus time or velocity versus time graphs in any way. Yeah. Okay, and then obviously because we're drawing an arrow, we can make the arrow point in the direction the vector is heading. Okay, that's the whole reason we use arrows. And we just use lines if we weren't worried about which way they're going. Okay, but we want the arrow to point in the direction the vector is heading. Okay, so in this case here, we've got a vector that is 2 kilometers in length, and it is going 30 degrees north of east. Why did I say it that way?
Because it's more horizontal. It's closer to east than it is to north.
Yes, it's closer to east than it is to north. In other words, the 30-degree angle was measured from east. It moved north of east, and that's why we say it that way. Okay? So we always have to look at where is my vector. I could have just as easily said, if there wasn't a compass here, I would have said this is 30 degrees above the positive x-axis, because that would also be true. That would be a relevant vector, except that they told me, because of this compass, that it's obviously a compass direction and not an xy plot. Okay? All right, so we write these always as something of something. So when we're talking about our directions, especially when it's compass directions, this one would be north of east because my angle is touching due east. It is measured from due east, so it's north of east. This could have also been written as 60 degrees east of north. That would be exactly the same direction, okay? But it wasn't measured that way. It was measured from east. Okay? Now, what some people do is, like what I always do is I always draw out my vector like this, and then I go, all right, I'm on east, and I'm going north. Now I know it's north of east. Some people are like more like kinesthetic learners, and so they do like, they get their hands going. It's kind of funny to watch on final exam, because you see people and they're looking around, make sure no one's looking at them. You're still doing that. And that's fine, there's nothing to be ashamed of. It's whatever works for you, okay, you do. Okay? But if you're doing that, okay, this is north of west, okay, and this is east of south, and they're getting their hands all twisted around, but it works, okay? Whatever way works for you. Okay, so big things, the direction of the arrow, okay, gives the direction of the vector, and then, okay, the length of the arrow is proportional to the magnitude of the vector. So if I had a 4 kilometer long vector, it would be twice as long as that arrow. All right, does this mean when we're doing vector diagrams that I have to have a ruler and a protractor and all of that kind of stuff? Please don't. Okay? Your scale, you have to have scale, but you don't have to measure it every time. It'll take you forever if you are physically measuring every line, figuring out what the scale is going to be, and then putting your protractor on there and don't. It's so not worth it. Okay? It doesn't matter that much as long as you're somewhat accurate. If it's supposed to be a 30-degree angle, make sure it looks somewhat like a 30-degree angle and not a 70-degree angle. Okay? And then your diagrams will work out just fine. But you definitely do not need to measure and scale every single one. Okay? Just draw them approximate. You'll get the hang of it and it works just fine. Okay? When people get messed up on a question, it's usually because they didn't take their time to draw it at least approximately to scale. Okay? And they've got a 10-kilometer line that's twice as long as their 8-kilometer line. Okay? And then their diagram looks different than their answer. Even though their answer is mathematically correct and they did everything right, they look at the diagram and go, well, that can't be right. My diagram doesn't look like that answer. Because we all automatically assume we did the math wrong. Because math's hard, that's what we think. It's not true, okay? But that's what we think, right? We right away go to, I must have done the math wrong. It couldn't have been that I drew a picture incorrectly, because anybody can draw a picture. It's so not true. What most people screw up is the picture, okay? Most of the time, your mistake is not with the math. Okay? Most of the time, the mistake's with the picture because we believe we can draw, but we don't believe we can do math. Real problem. Okay? So believe in your math. It's easy for me because I'm not all that good at math, but I really suck at drawing. So I know if I make a mistake, I can look at the drawing, but I probably screwed that up. All right. So often it's necessary to add one vector quantity to another. Now, when I say that, I mean like 2 displacement vectors, or 2 acceleration vectors, or 2 velocity vectors. I'm never going to add a force vector and a displacement vector together. Okay, that's like adding apples and oranges. I don't know what you get, but it's nothing. Okay, so you're not going to ever do that. The 2 vector quantities have to be the same kind of vector quantity. Everyone okay with that? Because I sometimes see people do that. They put displacement and velocity in the same diagram, and they're adding meters per second in meters. And I don't know what that calculates, but it's not right, whatever it is. Okay. So what we do if we want to add vectors is we simply draw the 2 vectors as arrows, and then we draw them kind of chronologically, okay, or like we're telling a story. So first, in this example, the car goes 275 meters due east, and then another 125 meters due east after that. Okay, so what we do is we first draw this line here, and we say it's 275 meters, it's pointing due east, and then after that came this 125 one. Okay, it's also due east. So this happened and then that happened. Okay, is that all right? Okay, so I drew them tail to head. One happened, then the other happened. Now, this can get confusing if you have something happening at the same time. That would never happen with displacement vectors because you can't go two directions at the same time. Okay, you're not like Don Quixote who got on his horse and rode off in all directions. Okay, or like this scarecrow in the Wizard of Oz, right? Some people like to go this way, and some like to go this way, and some like to go both ways. You can't. Okay, there's in displacement vectors and velocity vectors and acceleration vectors, you can't do two at the same time. The only vector quantity where you might have two things happening at exactly the same time would be force. If two people are pushing on the same object at the same time, you have two forces acting on it. Okay? It still doesn't change what we do. Okay? Vector quantities are always going to be added tail to head. So I'll give you an example. Let's say I have a box that has a mass of 100 kilograms. One person is pushing it this way with 300 newtons worth of force, and one person is pushing it this way with, let's also say 300 newtons worth of force. Which way is that box going to move? At an angle, right? 45-degree angle. Okay, so this isn't a proper vector diagram because I have not drawn these tail to head, have I? I've drawn them tail to tail. But look what happens if I draw them tail to head. I get an arrow that points in the direction that box was going to go. Okay, that's how vector addition works. Okay, it doesn't matter whether the vectors happen A, B, C, or whether they happen at exactly the same time. They're always drawn tail to head, and they'll always tell you what the overall result of those vectors is. That's why we call it the resultant. Okay, this line that I drew right here that connects the beginning to the end is my resultant. Okay, we always call it the resultant, but it's always going to represent something. If it's two displacement vectors, then the resultant represents the total displacement. If it's two velocity vectors, then the resultant represents the average velocity. If it's two acceleration vectors, the resultant represents average acceleration. If it's two force vectors, like this, it represents the net force. Okay? Everyone okay with that? Okay, but that's always how we get our result. We draw the vectors tail to head. It doesn't matter whether they're perpendicular, collinear, or totally random in direction. Putting them tail to head is always going to give us a starting point and an ending point that we can connect, and that connection will show us what the overall motion resulting is. Okay. So this is just a continuation of what we were looking at before. So I have that 275 meter vector that was due east, that 125 meter vector that was due east. So that means my total displacement is 275 plus 125 is 400 meters east. Okay? That's it, that's all there is to it. Okay, when we're adding collinear vectors, it's really easy. I'm either adding them because they're in the same direction, or I'm subtracting them because they're in opposite directions. That's the stuff you did in Science 10. You just never drew pictures of it in Science 10. All right, so it's important to remember that all vectors are drawn tail to head, and all vector addition is done in that manner. It doesn't matter what vector quantity we're adding, it's always tail to head. Mason, question? You may. Okay, any questions on that one? Okay. What happens if they're perpendicular? So now this car goes 275 meters due east, and then it goes 125 meters north. So I still draw them tail to head, because we said it doesn't matter what kind of vector quantity it is, we draw them tail to head, but now they don't point in the same direction. Is that okay? Yes. Remember, my total distance traveled, which is a scalar quantity, is still going to be 400 meters. I went 275 and then 125. My total distance is still 400. But now, this was my initial position, and this was my final position. The line that connects them represents my total displacement. It's my change in position with magnitude and direction. All right with that? But now, I can't get that by going final position minus initial position, because they're not collinear. So how do I figure out how long this line is?
It's the a squared plus b squared is c squared.
Right. Use the Greek geek. Okay? Pythagoras is the Greek geek. Spent his whole life studying triangles. Okay? So he's the Greek geek. Okay? So we use Pythagorean theorem, and we will get the magnitude of that line, its length. That's only part of our answer, because obviously displacement needs magnitude and direction, but that's the first part. So to calculate what our total displacement's magnitude would be, we take 275 squared plus 125 squared, and then we take the square root of that. Okay, so my total displacement is 302.08 meters. I'm keeping all those decimals in my calculator for later. What did I say, 0.08? Is it meters? Yeah, meters. Okay, so there's the magnitude. How do I figure out what direction this thing is going?
The angle between like the resultant line and the one on the bottom.
This?
Yes.
Okay, so I gotta find that angle. I know all three sides of my triangle. I really have my choice of how I get it. Okay? For me, my choice would be to use the numbers I was given in the question rather than the one I calculated, just in case I messed that up. Okay? So, how do I use this side of the triangle and this side of the triangle, which are the opposite and adjacent sides to this angle, to get the angle?
Sine or
I would use tan. Yeah. Okay. I would use the trig function tan. Okay, because tan of theta equals the opposite side divided by the adjacent side, and I have those two sides. I know the opposite side's 125, and I know the adjacent side is 275. Okay. Everybody all right with how I picked which one was opposite and which one was adjacent? So I want to calculate theta. So I have to manipulate this equation to solve for theta, not the tan of theta. So I bring tan over here, and what I end up with is theta equals the inverse tan of 125 divided by 275, opposite over adjacent. Okay, so second tan, and you got to make sure your calculator is in degree mode. If it's not in degree mode, it's really going to foul stuff up. 125 divided by 275. Okay, so that angle is 24 degrees. Which way? 24 degrees north of east. Right, the angle arc I drew is touching east, so it's going to be of east, and it's going north of east. All right, so my final answer can have 3 significant digits, right, because I was given 125 and 275, both of which have 3 significant figures. So my overall displacement will be 302 meters at 24.4 degrees north of east. Okay, since I had already calculated the hypotenuse, could I have used any of the trig functions to calculate that angle? I could. Tan's my favorite, so I use it all the time. That's when you know you're on a different level of nerdy when you have a favorite trig function. Okay? That's okay, I'm comfortable with myself. Okay? I can manage that. All right, everybody follow what we did there. Right? I mean, is there anything like really mathematically challenging about what we did? We did a Pythagorean theorem calculation, and we did a trig calculation, and you've done trig before. Okay? It's not, terribly complex stuff. It's a matter of just plugging in numbers and recognizing what sides of a triangle are what. Okay? Hypotenuse, opposite, and adjacent, and that's all relative to the angle that's drawn. All right. So everybody's okay with how that went? Okay. So this is the gist or the basis for all vector addition. We want to make all vectors essentially right angle triangles. Once we can resolve any vector into a right angle triangle, we can get anything we want from it. Okay? We can get all the sides, we can get all the angles, all of that kind of stuff. And that's why when we're dealing with vectors that are not perpendicular or not collinear, why we have to figure out their horizontal and vertical parts. Because we need to figure out how far over and how far up does something go, even if that trip has more than 2 or 3 parts. All right, so this is all the stuff we just did here. Okay, just written out neater. All right, everybody okay with that? Okay, now I'm going to show you where we're headed. Okay. I'm going to write a question on the board here, and I want you to write it down too. And then we're going to go through how to solve it. You know what? I don't want to do that yet. I want to go over some simple ones first. I don't want to throw you yet. I'm going to do that one in a minute. Okay, so in this one here, this is a super easy. I would have given you this like the second day of physics and science 10, so it's super easy. So these contestants who live in the most boring town in the world, okay, do this snowshoe race where they move forward 10 meters and untie a bunch of knots, and then move forward 5 meters and solve a puzzle, and then move forward 25 meters to the finish line. Determine the resultant vector by adding the vectors graphically. That doesn't mean using a graph, it means by drawing a graphic, drawing a picture, vector diagram of this situation. So this situation looks like this. 10 meters. 5 meters. 25 meters. Okay, did I take the time to measure those lines? Are they at least somewhat to scale? They're good enough. Okay, and that's generally what you need for a vector diagram. Again, you don't have to measure everything out. Okay. So my total displacement here is going to be 40 meters forward. You will never get one that easy. Because that's ridiculous. Okay. Okay. I want you guys to try number 6. I'll give you a few minutes on number 6. Okay? Draw a vector diagram of it. Okay? And see if you can figure it out. Okay. They say draw a vector equation. You could also do that with positives and negatives. It is all collinear. Okay, in the end. Okay, so on number 6, they're just going forward and backwards, so it's nothing too terribly stressful. Okay, so they do a tough drill on this field that's a length of 100 yards. Players run to each 10-yard line and back to the starting position until they reach the other end of the field. Okay, so we've got okay? Like to 10 and back, and then to 20 and back, and then to 30 and back, okay? And then to 40 and back, and then to 50 and back, okay? To 60 and back, okay? To 70 and back, okay? And I'm drawing these not tail to head. Why? Because my diagram would look like this. Because I keep drawing right over top of the line, 'cause it's just forward and backward. Okay, so I'm just kind of setting them apart from each other. Okay, in the end, okay, if I want to calculate the total distance, okay, I've got to add all these lines together. Right, so that'll be 20 plus 40 plus 60 plus 80 plus 100. Oop, that was times. Plus 100 plus 120.
That was time.
Times
I did times again. Sorry. Okay. Plus, okay, 140 plus 160 plus 180 plus. Did they end up? They go all the way. They come right back to where they started, right? No, the other end of the field. Okay, plus 100. Okay, because they don't come back. So it ends up being a kilometer worth of running, which is pretty far. Okay, that doesn't sound like a drill that's much fun. All right, what's their total displacement?
100 yards.
100 yards, I would say downfield or forwards. They don't really describe it, but they do say on the field, so other end of the field, towards the other end of the field could be a valid vector there. Okay? We have to give something. All right, now, this next question I'm going to have you try is both a vector, but also a question that makes you think outside the box. It's actually an algebra trick. Okay? So it's a bit of an algebra trick, but it's also a bit of vectors. Okay, so I want you to try number 7, but you got to read it carefully if you're going to get it. Okay, so a car drives north 500 kilometers, and then it drives 3 sequential displacements south, each of which is 50 kilometers longer than the previous displacement. The final position of the car is 50 kilometers north. Find the 3 displacements. So find the length of each part of the return trip. Okay? I'll give you a tip. The first part of this is figuring out how long the return trip is. Okay? Remember that those 3 displacements add up to the displacement of the return part of the trip. Give you a little bit of time on that. So for this one, we know it goes 500 kilometers north, and when it's all done backtracking, it's still 50 kilometers north of where it started. Okay, so the trip in a vector diagram looks like this: 500, okay, and then 450. Now this 450 is broken up into 3 sequential lengths, each of which is 50 kilometers longer than the one before. Okay? But I don't know how long the first one is. All they tell me is each one is 50 kilometers longer than the one before, and there are 3 of them. So what I'm going to do is set this up algebraically. These 3 trips add up to 450. What they have in common is the length of the first leg, which I don't know. So I'm just going to say x. How long's the next leg?
X plus 50.
Right. The next leg is x plus 50. Okay. How long is the next leg? X plus 100. They all had x in common. Now, how many x's do I have on that set? 3. Okay, so I know that 450 equals 3x plus 150. So I'm going to subtract the 150 over to this side. 300 equals 3x. How big is x? 100. So first trip was 100. And then the next one was 150. And the next one was 200. And then it's up to 450, and that's why it works out. It's an algebra. Right? But it's still a vector thing. It's still important to be able to get that 50-kilometer overall displacement so we know that trip's 450 kilometers long. I would never give you one like that on a test because I feel like it's more of a math question than it is a vector question. Okay. This is a good one for us to go through, so I want you to write it down. Okay, and we're going to walk through how to do it together. It's a perpendicular vector question, kind of like the last one that we did, okay, with the right angle triangle. Okay, I want you to write it down, and then we'll go through it here by drawing out the diagram and getting all the stuff figured out. So what we want to start out with is our vector diagram. Okay, we know these are 3 displacement vectors. We know they happen one after the other, so we need to draw this like we're telling a story. She first goes 0.8 kilometers south. Then she goes 1.2 kilometers east. And then she goes 0.3 kilometers north. Okay, that's a decently to scale. Okay, at least close enough for what I need to do. All right. So I've drawn those 3 vectors, tail to head, like I'm supposed to. Question wants the total displacement. Where would I draw a line on that diagram that would represent this person's total displacement?
From the tail of the 0.8 kilometers to the head of the 0.3 kilometers.
Exactly. From their from their initial position to their final position. That is, after all, what displacement is supposed to calculate, their change in position. So that line there is my resultant displacement over the entire trip, or this person's resultant displacement. Now that doesn't make a triangle. Actually it does, we just haven't drawn it yet. Okay, if I want to calculate how long that line is, I need to put it into a triangle. Would you agree? Okay. Can I do that by figuring out how far north, south, east, west she goes? How far east does she go? 1.2 kilometers. All right, so I'm going to draw what we call a vector component. Okay, this is the east or horizontal component of her entire trip, and it is 1.2 kilometers east. And I draw it also as an arrow. How far north-south does she go? 0.5 kilometers. Which way? South. All right. I got a right angle triangle now. Can I figure out how big that displacement line is? Yes, I can. Okay, so I'm going to go to the Greek geek, and I'm going to have him figure it out for me. Okay, 1.2 squared plus 0.5 squared will give me the magnitude, at least, of her total displacement. All right, her total displacement is 1.3 kilometers. That's the magnitude. What else do I need? Direction, okay. Where would I draw an angle arc that would tell me the direction she goes?
You draw it from where the black and the green arrow intersect.
Okay, so would I draw it in here or in here? I could do either. The problem is, if I do it here, I don't have a triangle that includes that. Okay? So what I always tell people to do is if they're not sure which angle to find, circle your starting point. And wherever that circle goes through your triangle is the angle you want to find. Okay, so I want to find this angle here. Now, which trig function should I use? Any of them. I have all three sides. Okay, I can use sine, cos, or tan, but tan's my favorite, so I always use it. Okay, so tan of theta equals the opposite side over the adjacent side, so that's going to be 0.5 over 1.2. I want to find theta, so that'll be tan to the minus 1 of 0.5 over 1.2. All right, so that is 23 degrees. Which way? South of east. Yep. Okay, because this angle arc that I drew here touches due east and moves south of it. South of east. I could have also said 67 degrees east of south. Either one of those is correct because they are the same direction. Okay? Everybody all right with that? Okay? So that's about as tricky as a perpendicular vector would get. Okay? We're going to be dealing with ones that are neither perpendicular nor collinear starting tomorrow. Okay? So we're going to be dealing with, I just need a blank slide. Okay, there we go. Okay? We're going to be dealing with something like this. Okay, so far, same rules apply. The wording of a question like this would have been something like this. A plane flies 10 kilometers at 40 degrees south of east, then turns and flies 18 kilometers at 30 degrees east of north. Okay, that's probably not 30 degrees because they didn't do the scale very well, but we'll just say it is. Okay? What's the overall displacement of the plane? Where would I draw a line that represents the total displacement of the plane? Daryl's doing this at the back. And he's exactly right, because no matter what you do when you just draw it freehand, you're right. Okay, so it would be from the initial position to the final position, which is over here. Okay. If I want to calculate the magnitude and direction of my overall displacement, I need to know how far east and how far north this thing goes in total. Agreed? I would need to know essentially that triangle. Okay, now, how do I go about getting it? Not sure?
No, I'm
Doing it differently? Okay. Since I know the magnitude and direction of the two vectors that contribute to this, could I figure out how far east and south the green vector goes, and how far east and north the red vector goes? Okay. what would I use to find out the sides of those triangles? How many pieces of information do we need to know about a triangle to find out all of its parts? 2. You either need one side and an angle or 2 sides. Okay, 2 angles, I guess as well. Okay, we never do it that way, but okay. In most cases, we have the hypotenuse and an angle. If I have the hypotenuse and the angle, I can use trigonometry to get the adjacent side, which would be this one, and the opposite side, which would be this one. Okay? I can use sine and cos in order to get the sides I don't have because I know the magnitude and direction of the hypotenuse. Okay? That's what we're going to be headed towards tomorrow. Okay? Is being able to resolve a vector into its x and y components. Okay? So this would be, this side here would be green x. This side here would be green y. This side here would be red x and red y. Okay, and here's where we go from there. Once we find those, if I take green x and add it to red x, do I get blue x? Okay. If I add green y and red y, do I get blue y? I do, as long as I make green y negative, and it is, it's south when the other one is north. Okay, that's where we're headed. Resolve into the x's and y's, and then use the x's and y's to get the big picture. Okay, so the diagrams get a little crazier, but the fundamentals are still the same. All right, good work today, guys.